really been a wonderful conference. I mean, the science has just been fantastic, and I've learned a lot. It's nice to see old friends make new ones. Really appreciate the invitation to come here. The organization has been so wonderful as to be invisible. It's just a great few days. So, it's the last talk of the day, so my goal is to run out of time before I have to do anything hard. I'll make sure to ask what the beeping means. So anyway, our goal is to illustrate how techniques of Teichmüller theory may be applied to prove existence, and then implicitly uniqueness and some non-existence theorems for minimal surfaces in Euclidean 3 space. I hope this is legible. Not sure what to do if it isn't. Anyway, so why this approach? Well, there seem to be many embedded minimal surfaces of high genus, which, for instance, have fat handles. So so we've seen from work of from discussions of Matthias and Peter and others, citing work of Treize, how implicit function techniques can open up small handles from degenerate configurations. But of course, we only get an epsilon's worth of surfaces there, and one expects those to continue for some time and to develop fat handles, or maybe there are just surfaces out there which can't be degenerated, which have fat handles. So we would like to have techniques to prove existence theorems when the implicit function theorem techniques, when the regeneration doesn't apply. And these surfaces with many handles, I want to produce high genus minimal surfaces. They're unstable, and we've seen from other talks that PDE can be very hard. And so that's just, and I got to eat, so I got to do something. I can't do the PDE. So that's the idea. What I'd like to, so the technique I'm going to use is the virus truss representation, which I'll explain one more time. The disadvantage of the virus truss representation is that it produces only immersions. So it's a local technique, and I'll explain this again. And so, as I said, we don't have we avoid some of the difficulties of the really careful PDE stuff with embeddedness, but the problem is that one doesn't get embeddedness unless one works, and at present there's only sort of ad hoc techniques to prove embeddedness from the immersions that get produced, and that'll be shown today too. So here's the sample result I want to talk about today. So I want to take, the classical Shirk surface and add as many handles to it as you wish. It's a doubly periodic surface. So I need to show the Matthias pictures. So let me take these away. So I want to show a family of doubly periodic minimal surfaces with quotient genus is G, so it's G handles. And they have two ends, and unlike the Peter Connor talk, the ends here are orthogonal. So some go up this way, and some they go up this way and go down that way. So I'll show those pictures. So so of course this is classical Shirk surface. So we want to add some handles. So here we've added a few, or Matthias has added them. I loved your work in Avatar. Anyway, and then couldn't resist. And then here's some more handles, and then the guy quit on me. So we've done the same sorts of techniques Matthias and I have used before, and I'll might as well give a tour. So we started off, we gave some, let's see, so let's try it this way. I don't know which is better. So yeah, the other way. So the surface at the top, this surface here is, at the top left, is a surface that has the end of the classical Enneper surface in one handle. That was known before, Chen-Gagstetter. And this one has two handles. That was also known before, also Chen-Gagstetter. And this one has four, and this one has more. And so showing that we could get arbitrary many handles that uses the same techniques was also done at the same time a little earlier by Sato. My student Sumin Kim has shown that this sort of surface, this one takes a limit, converges to something, and we expect that something is Shirk's singly periodic surface, just has the handles evenly spaced. So just to keep talking about this sort of, as long as I'm showing pictures, my student Casey Douglas has taken the original, let me back up, and look at these one-handled surfaces, which is also due to Curvature. I think that's one-handled. And again, we have, in this picture, the ends are orthogonal. Some are going up this way, and some are going down that way. And so what Casey did is that he sheared that lattice. So all of this was over a square, and so one could hope that you could shear the lattice till it became as through rhombi, and then just keep going. And that's what Casey did. He did it in genus 1. It was also done at the same time by Baginski and Batista. So that's sort of a view from above. You can see the rhombus. I should say it's genus 1, so be nice to do it in all genera. It's quite non-trivial. The problem is that, of course, there's more symmetries for a square than there are for a rhombus, so one has to break symmetries to do this, and it was quite a tour de force on his part to accomplish that. And then, of course, he kept going. One can just keep that rhombus going and take a limit. And so he did that as well. That's an impenetrable picture that starts to show that what one gets is a singly periodic genus 1 helicoid in the limit. So, so the question is, I guess one thing I should have highlighted here was that you saw the handles were thick. There weren't the small handles. And that's the issue, is to try to find techniques that would allow you to get the thick handles. And the main technique is the Weierstrass representation. This has been explained a few times. So Bill started already. Let me add just a little more detail to it for folks who still haven't quite gotten it yet. The point is that Bill pointed out that the coordinate functions x1, x2, x3 restricted to a minimal surface are harmonic. So what does harmonic mean? It means, write it Laplacian in complex terms. The d bar d of each of these coordinate functions is 0. So if I read that one step at a time, it says if you looked at the complexification of dx1, for instance, so round d x1, that's a holomorphic form. So of course, once I start with round dx1, I can get dx1 by taking the real part, and I can integrate the real part and get x1. So if we can find good forms, round dxi, to stand in for, if we can find good forms, then we can integrate those to get the coordinate functions in space. And that's what the Weierstrass representation does. It just finds 3 good forms, which when integrated become the 3 coordinate functions. So that's the idea. So it's a clever way of writing round dx1, round dx2, and round dx3 for a minimal surface. So to do that, the ingredients are one needs a Riemann surface on which one can put holomorphic forms, a holomorphic function g, and a holomorphic form dh. Dh is a misleading notation. It's not necessarily exact, it's just a one form. And then what one does is you build combinations of those ingredients into 3 particular forms, which you can see. So this will be the dx1, this will be dx2, and this will be dx3, round d's. And so when one integrates them, we get 3 complex numbers. Take the real part, you get 3 real numbers, and 3 real numbers records where you should put your point into space. That's the idea of the Weierstrass representation. And the formula is built so that there's several features of it. The first is that, of course, the coordinate functions are harmonic because they are they come from integrals of holomorphic forms. the map is conformal. That's just an easy check. And the ingredients are chosen to be simple and geometric. It's a formula if you've never seen it before, which is a little daunting, but you know, it fits about the length of my arm, so that's not so bad if you're going to study something. And it's, the G is geometric as it's the Gauss map, and the dH is just the complexification of D third coordinate, just round dx3. So if one understands the geometry of the surface that you're trying to create, one can guess or describe characteristics of the ingredients for the Weierstrass representation. So if I know that I want a few normals on the surface pointing up in a few places, then I know the divisor of the Gauss map. I know where dH has a 0. And from the divisor information for holomorphic data, you know a lot about the data. So that's really the game, is to somehow use your intuition or Matthias's numerics about a surface to understand the qualitative features of the Weierstrass representation of the ingredients for it, and then use those ingredients, because that almost determines the forms themselves, to build the surface. One issue is that there's often lots of parameters. There's a minor problem and a major problem. The minor problem is local. It's that when one looks at the metric that one gets by using this Weierstrass representation, here it is. You can read as well as I can. What you see is that there's G's of some orders and DH's of some orders. So there's some compatibility that has to happen between the zeros and poles of G and DH. That's easy to fix. The hard problem is that, don't look. The hard problem is that everything is local. So, gee, I'm glad I used that green letter. Anyway, so if one looks at the green gamma cycle here, well, if you look at a cycle, everything is local in that formula. It's all just about, it's a line integral. You start at some point and just integrate out to the point you're aiming for. Then a patch on the, so if one looks at just a series of patches along the curve, that might develop in space through the x1, x2, x3 coordinates to some curve that doesn't close up. It might just keep going. And when this patch goes here, the next patch goes along, there's no guarantee the thing will come around and meet itself. So in order for it to meet itself, when you go all the way around, you have to get back where you started from. So that's what's been referred to as this period problem, which is that all of these cycles, all of the forms must have periods as you go around the curves, have zero real parts, so that there's no periodicity as you go along. For the periodic surfaces we'll talk about, one needs to control the periodicity, but in general, one wants to have it go away, at least be under strong control. I was raised in Teichmüller theory, so I do complex, and so I try to look at things complex analytically. And so it's a convenient rephrasing that to rewrite these period conditions in terms of that if one looks at the forms you create from the G and DH as GDH and 1 over GDH, that those periods should be conjugate. That's an algebraic reformulation of this. The third one just comes along from the ride, and in fact, actually, in many situations, like in the one I'll talk about, doesn't figure in at all because of some exactness. Okay, so we have these ingredients of forms GDH and 1 over GDH. Take those as our ingredients now. We only need 2 ingredients. Doesn't matter what they are. And we have this condition that sort of separates out the 20th and 21st century minimal surface people from the 19th century ones, which is the effective topology and trying to control periods of cycles on surfaces that have some complexity to their topology. And the question becomes, how should we understand these periods? And how can you come to grips with them? And so the perspective I want to take is that of looking at flat structures that correspond to one forms on Riemann surfaces. So the idea is that if you have a holomorphic one form, like GDH or 1 over GDH, then you can look at its absolute value. So that's going to every tangent vector record a non-negative number. And that's a line element. So every tangent vector I get a number. So that's a way of measuring infinitesimal length on the Riemann surface. And if you check, because the forms are holomorphic, that translates into the metric being flat. And the flatness, and that's true. It's an easy computation. Except, of course, at the zeros, there's always issues. And at the zeros of the form, or the poles, the metric has cone angles. So instead of having a circle having length 2 pi epsilon around it, it may have 6 pi epsilon at radius epsilon. So, for example, if I had z squared dz, pen needed a new pen at this point, sorry. Then when I look at z squared dz, or like r squared times the Euclidean element as a line element, then this has a 6 pi cone point at the origin. So rather than sort of explain the theory of this, let me give you a nugget to take home, which is how I started to understand this some time ago by stealing this from Thurston. So the question is, well, when I took first year complex analysis, I was introduced to the Weierstrass P function, which was an infinite series, and I found it somewhat mysterious. And so the question is, how does one, so if one's given a torus, which is often written as a parallelogram with identifications, and here I'm writing it in the W plane, then on that torus, there's this function, Weierstrass P function, P of W. I can turn it into a form by saying P of W dW. So what is that, and what are its periods? It actually just shows up in Costa's work. So how does one understand it? We're trained. It's funny, when you draw that parallelogram on the board or on the wall, and you draw the identifications, everyone looks inside it. Right? So you're trained to look at the interior of it, and it's a parallelogram. One could also look outside it. So what I'd ask you to consider is the exteriors of that parallelogram with identifications in the sphere. So on the plane minus the parallelogram, if you add infinity and then glue things up, it's still a torus. Okay? So, and we could look at the form, instead of looking at the form, I'll switch notation, dz inside, which is the non-vanishing holomorphic 1 form, we can look at the form dz on the outside, which is something else. And what do we know about dz on the outside? Well, it has a double pole at infinity. dz has a double pole at infinity, we know that. But at the vertex class, at those 4 vertices which are gluing together to 1 point, in the exterior, that flat metric, absolute dz, the Euclidean metric, glues together to have a cone angle of 6 pi. Right? It's 2 pi on the interior, there's 4 of them. So what's left over, 8 pi minus 2 pi, will be 6 pi going around the edges. So here I am, I'm adding up the angles around here, around here, around here, and around there, and that's 6 pi. So what that tells us is that at that point, this form dz, when it descends to the torus, has a double zero on the exterior. So that form dz has a double zero at infinity at one point, has a double pole at infinity, a double zero at another point, no other zeros or poles. So that exterior is the virus is P of W dW on some other torus. So if what we're going to try to do is go backwards. I'm going to have some mysterious form here. I'm going to try to represent it as some nice dz on the exterior of something else, or on the interior someplace else, some other domain. And this has the advantage because of the following, is that if I want to understand periods of P of W dW, so maybe I have some cycle in the, I'll just do it. So maybe I have some cycle in this W parallelogram, gamma, and I want to know the integral of P of W dW along it. Well, I know that to be some other cycle on the exterior, But P of W dW is dz on the exterior of this parallelogram, and I know how to integrate dz. It's just a difference in the endpoints. So if that cycle comes around here, the period of it is just the difference, just the side distances from here to here, the complex distance. So imagining forms as Euclidean metrics and developing them into the plane also displays their periods as complex lengths, and that's the perspective we'll exploit. Okay. Great. So I just wrote that. Periods of GDH are visible as some complex translation distances in the development of the flat metric into the plane. Okay. All right, so now let's prove the theorem. We go to Matthias and we say, what's this thing look like? We want to make a surface. Matthias produces a picture, or maybe if he's not around, we actually have to use our imagination. I keep him around. And from the picture, we have some understanding of what the divisors of the Gauss map and DH should look like. So, and we have some idea of the symmetries of the surface. Now, if I have a flat metric and I have symmetries, the fixed points of the symmetries have to be geodesics in the metric. It's a non-positively curved metric. Check that fixed points of symmetries have to be geodesics. So then once it's flat, geodesic is a straight line. So this tells us how, given some portion of one of these surfaces, some idea of how it should develop into the plane, how GDH, for instance, might develop. And it's actually fairly elementary to work out. And if I look at 1/4 of the surface, GDH actually turns out to look like this. I cut it by some symmetry lines. They'll be straight lines, and because of the orthogonality, they'll meet at what should have been right angles. And it'll develop into some portion like this, where these are the ends, and there's a certain symmetry about the center. And the periods are just visible. So what's the periods around one of these cycles? Maybe I should throw the picture up in a minute. The period is this much. So it's from here to here is the period of one of them. I'm a little afraid I'm being too mysterious, but so I probably won't get this right. But so for instance, if I take this surface, then the straight lines I'm drawing are going to be the images of, say, this curve. That's a symmetry line, and that will develop to something straight, and then it'll make a right turn and go to another symmetry line. And if I ask I can ask what's the period of GDH, say, around this handle, or maybe around half that handle, and it's visible on this surface as just one of these lengths. That's the idea. And so in some sense, I can solve the period problem immediately. If that's GDH and the periods are those complex lengths, then the conjugate periods, so the period for the same cycle for 1/GDH is going to have to be that same length, except heading down. So that means that the conjugate periods has to look like, in some sense, the reflected surface, so that, I almost did it right. So this one heads up and this one heads down. So the conjugacies of so once I know one development, I know the other one for free, and in some sense I've solved the period problem. Apparently with no work. But of course that's a lie. You don't get stuff for free. So the problem is not done. The issue is that even though we've written down 2 developments of domains for which the period problem is solved, there's no guarantee that the 2 domains were conformally the same. That when I lift back to the Riemann surface, that I'll get 2 Riemann surfaces that are the same. I just have 2 different surfaces with 2 different one forms, each of which has this period condition. There's some sort of relation between the periods, that the GDH on one is conjugate to the GDH in the other. So all we've done after all this work is exchange a period problem for a conformal problem. Okay, so this is where Teichmüller theory comes in, because Teichmüller theory is about how one moves Riemann surfaces, how one deforms Riemann surfaces, and understands how geometric quantities on those Riemann surfaces change. So, and this is like one of the world's simplest moduli space problems. Because what is the moduli space of domains I'm worried about, I'm thinking about? They're parametrized, there's dilations here, so it's fewer than you think. It's parametrized by just Euclidean distances. Like, I can parameterize all the possible GDH domains by that length, and that length. And once I know that's the origin, and I'm going to have to end up here, once I know those three numbers, I can draw this to here, and I end up here, I can go straight up and hit, and that just determines the domain. So our domain is, so the moduli space that I'm thinking about here is very concrete. It's just collections of three numbers that are more or less arbitrary. So the problem is to find the right three numbers so that this domain that I construct with those three numbers and the conjugate domain that I construct with the same three numbers is the same Riemann surface. There's some conformality between those two disks. Now, let me just, for the grad students in the audience who are taking complex analysis and hear me say, I want to know that two disks are conformal, of course, Riemann mapping theorem says that any two disks are conformal. But here, I need something special about the conformal map between the disks. This point on this disk is, if I were to do the sort of funny reflection here, is the same point at the corresponding vertex. So whatever conformal map I take from funny polygonally bounded disk to funny polygonally bounded disk has to take vertices to vertices. And I don't have that much freedom for my Riemann map. Usually just get 3 points. So the plan of the proof is that we're going to do some Teichmüller theory. So let me tell you the architecture, I haven't done anything yet, I haven't done anything hard, is I want to find a height function on this moduli space. And I want the height function to vanish. I want to have a 0 for this height function, be at the bottom. It's positive, non-negative height function. And when I'm at the bottom, when height's 0, I want to have my problem solved. So the GDH domain and the conjugate one I built by the sort of funny construction of flipping everything over should be the same. When I'm not 0, I want to have a gradient flow. I want to be heading down. And I want the function to be proper. And that's enough, if you just think about it, to know that I'll always have a solution. So I'm either at 0 and done, or I'm not 0 and I have a direction to go to get lower. And so each of these is a sort of distinct type of deformation. So let's see if I can fit them all in. So I need to have some sort of complete set of conformal invariants in my height that my height function is measuring differences between, so that when the conformal invariants are the same, though, like in some sense conformal lengths is really what we're going to use, then the domains are the same conformally. I need to know what happens to the domains as I do infinitesimal, as I do small moves to it. If I change the domain a little bit, how does that affect the conformal structure? How does that affect the conformal invariance? So I need to know how to take derivatives in this moduli space. And finally, I need to know, for properness, how to take asymptotics of these invariants. Most of these things were worked out in the 50s, 60s, and 70s, so they're all sort of available in Teichmüller theory. So let me tell you, I never thought I'd get there. I think someone broke your clock. So, so here's some technical aspects of the proof. What we'll do is we pick enough cycles, and here I'm supposed to be drawing 3 cycles. So I picked 3 cycles. It's maybe not important what they are. That will be enough to tell me all the conformal data on the surface I need. And then I have some notion, and then the height function is going to be some sum of heights associated to this. And the heights are going to blow up if the conformal invariant, which is technically called extremal length, if the extremal length of one of the, so the height of the cycle gamma I will go to infinity if gamma I in GDH or 1 over GDH, if that extremal length either goes to 0 or infinity, or, and this is probably what's going to happen, if it goes to 0 in both of them, but at different rates, or goes to infinity in both of them, but at different rates. And that the rates and the geometry, this is one of the technical parts that we do, or the observation, is that these will go at different rates because of the conjugacy. I can't say much more about that, but the point is that, remember, if one look back at the picture, in one cycle, in one picture, in one GDH, like the angles are going up, so we have like a 3 pi over 2 angle, and the corresponding angle is going down, so we have a pi over 2. And that's flip produces a sort of conjugacy in the data that defines it in the Schwarz-Christoffel map. And when one looks at the development, and when one looks at sort of the monodromy that comes from Schwarz-Christoffel maps that might do this, one sees that forces different rates of blow up. You can also just do it by hand and just compute integrals, but there's a real geometric reason that the two things are sort of incompatible. They sort of can't be simultaneously real analytic. So that's what accounts for the properness. To do the rest of it is a little it's actually trickier than I let on. Back up. So let me back up to a picture. This here. So in one of these domains, you might notice that in some sense a high genus has some relationship to low genus. In other words, this is a genus 3. If I had a less bumpy curve, I had a polygon that had, instead of having, however many it says, 8 segments in the top, it had 6, that'd be a genus 2 polygon. So in some sense, these moduli spaces fit together into a complex. So so you can think about the complex of moduli spaces, and that's what I'm drawing here, which is the lower genus moduli spaces are faces of the higher genus moduli spaces. And so the proof actually proceeds by induction. So what we do is we'll start with some solution there in the lower genus, and that's conformal in lower genus, and then we'll sort of open up a small little notch to move into the higher genus moduli space, keeping all of the heights that we had equal, all of the cycles that we had equal in the lower genus in higher genus but 1. And then we just have to get one of them right. And the way we get one right is by a very simple observation. That's a little misleading. So the genesis of it is a simple observation, which is that these domains actually fit together. If you flip them around and put them in, because the conjugacy of periods, because the lengths are the same and the orientations are just different, you can assemble them. And when you assemble them, you see that if I make a move in one of these moduli spaces, and what's a move? A move is just to make like A a little bit smaller or B a little bit bigger. So it really just sort of moves one edge a little bit. Then what happens is moving an edge a little bit eats into one domain while enlarging the other. So some lengths, like a length that might start at this edge, is going to get smaller because it gets something cut out of it. And a length that ends at the edge is going to get longer because it's got stuff added to it. And so that's how, if we're not the heights aren't in balance, then you can sort of make them be more in balance by flowing in this way. And the sort of technicalities of Teichmüller theory tell you how to do that. And so that's the 3 ingredients of the proof done in a way where I can pretend I told you about them, but you can't possibly check. So, and it leaves just, so that's existence, and this gives us an immersion using this sort of Teichmüller theory. I found good Weierstrass data which accomplishes the geometry that I wanted. It gives an immersion. It's not clear what to do here. We have no systematic way of moving from an immersion to an embedding. So everything is ad hoc, and sometimes it works and sometimes it doesn't. So this is a real weakness of the approach, is that embeddedness, if it's done at all, is always done in some ad hoc way. And here, the ad hoc way is the following. We look at a quarter of the surface. If you look at its conjugate surface, which is something we pull out of the air, so change the ingredients on the Weierstrass representation from R, G, and DH to R, G, and IDH, and see what you get, then the quarter of the surface I was looking at becomes, one can check, a minimal graph over a convex domain. Just happens because of the way the contour is set up. And then there's a theorem which says, a theorem of Kruse, sort of amazing theorem, which says that the original surface patch was embedded. You pull that out of the air and that proves embeddedness. Okay, thanks for your time. So extremal length is a conformal notion of length. What one looks at is, and it's in some sense, it's spiritually related to entropy in that you look at all possible. So I'm sorry, let me back up. What's a conformal structure? Conformal structure is all possible metrics that are related, that are proportional to each other, related by a function. So any quantity I write that and apply it to all conformal metrics is a conformal invariant. So here's what you do. You look at, for some class of curves, you look at pick a metric in the conformal class, look at the shortest distance in the, I can see what I'm doing. One has a domain, and you pick out some family of curves on the domain, say everything that connects up from here to there. And then one looks at all metrics on this domain which are conformal to the background metric, and look at the shortest length of any of those curves. And the quantity to look at then is the minimum of length squared over all the curves. And then this is length in a certain metric. Divide that by the area of the metric. So for each metric, I have a number. And then, of course, I have to do something that works for all conformal metrics. So look at the soup over all these metrics. And that's some number that has something to do with the conformal structure, but not the metrics, because I took a soup over all conformal metrics, and something to do with the curve system. That's called extremal length. It's been studied for a very long time, at least in some sense systematically since Berling and Alfors in the 40s. And those provide a complete set of conformal invariants for polygonally bounded disks. And one knows how to take derivatives of lengths of those, and one knows how to compute asymptotics of those, and it's a relatively easy invariant to work with.